So thank you very much for having me and for coming to the talk. Today I'm going to talk about this project that we finished kind of recently in collaboration with a lot of people, although I must say that the leading force was Samuel Scarlett, so the first one that I'm writing here. And today we will talk about three things. So just, among all these co-authors, Omar is also here in the audience, well, all the others very well known. And I will talk about three things today. So I will talk about the Markov entropy decomposition and how we can use that to, first of all, classically estimate the free energy, and secondly, to do quantum Gibbs sampling. Before that, what I want to do is introduce a little bit of the setting, because I'm sure that not everyone here is extremely familiar with this kind of setting, although, well, I'm sure that everybody has heard about that. So I will be working with spin lattices all the time. So just finite spin lattices, this is what I denote by this. So a finite subset of set D. Typically, I'm going to consider this a square structure because it's simpler, but otherwise, some of these results can be extended to more general graphs. And then the Hilbert space that we will typically consider is going to be the tensor product of all the local Hilbert spaces of all the sites. So it's going to be, I'm going to assume that all of them have the same dimension. And I'm going to assume then that we have a tensor product of all these ZD. And finally, we will talk a lot about density matrices today. And well, everybody's familiar with density matrices. The only thing that I want to highlight here is that I will use this notation to denote the subindex, with the subindex, the system where I'm considering the density matrices. So this is something that will become important later during the talk. And this is just to describe what I'm talking, what I'm saying when I'm mentioning spin lattices. But of course, the main object that we will consider, the main observable that we will consider in this lattice is going to be a Hamiltonian, which is going to be a Hermitian operator of the sum, of the form of a sum of local terms. So sum of local Hermitian operators supported in subregion X. And we will assume that our Hamiltonian is always going to be finite range or has k-local interactions, which is what I'm writing here. And this essentially tells us that if the diameter of these regions is too large, so if it's larger than a certain quantity that is this k, then all these terms essentially vanish. And all of them have a norm bounded by a constant that we call the strength of the interaction. So what this is telling us is that now our Hamiltonian is going to be the sum of patches, like the ones that I'm writing here. So when you consider this throughout the whole lattice, it's essentially going to be a sum of patches like this that are going to overlap and in principle can have different sizes, but the important thing is that their sizes are not too large. And sometimes we will, on top of that, assume this commuting condition, which means essentially that every pair of interactions has to commute. And the reason for that will become clear later. Let me just say that, of course, when we have one interaction here and one interaction here that don't overlap, this condition is totally trivial. But when these patches overlap, this is actually something that is highly non-trivial and is highly restrictive, but nevertheless is something that we have to assume in some cases. Okay, so this is the bare setting we are starting with. And the main object that we will consider in this talk is the Gibbs state. So we will consider the Gibbs state of this Hamiltonian at a certain inverse temperature beta larger than 0. And this is just going to be written by rho super lambda. It's important. I will emphasize this. Every time that I write a super index, that means the region where I'm considering the Hamiltonian. So essentially, now my Gibbs state is going to be, well, the exponential of minus beta h lambda normalized. But important that here I'm considering the Hamiltonian h sub lambda. Okay? So this is something that I will emphasize later as well when it appears. Okay, so this is the setting that we are considering, and now I was talking about a few things in the title of the talk, and one of them was the free energy. And what is the free energy? Well, the free energy essentially is considering this normalization factor, which is called the partition function, and taking minus log of it. So essentially the free energy is minus log of the partition function. And from now on, I'm going to omit beta from the slides because otherwise it's going to get so messy. So from now on, assume that beta equals 1. So in a sense, we are kind of absorbing it into the Hamiltonian. And now what we know is that if we want to compute the free energy, well, we can maybe directly compute it from here, but this is pretty inefficient. So one thing that we know is that there's a way to compute it variationally by taking this expression here. So we can take the minimum over density matrices of this expression, of the difference between the trace of the Hamiltonian and a certain state sigma, minus the von Neumann entropy of that state. And, well, this is a very valid way of computing the free energy. However, if now we want to do this in a computer, this is pretty bad. Why? Because the sigmas that we are taking here are exponentially large in the system size. So this is something that we are tracing out with respect to the Hamiltonian that is in the whole system lambda. That means that these sigmas are exponentially large in the system size, and therefore, if we want to use this for numerical approaches, this is terrible, essentially. So this is the starting point of this project. What we want to do is provide another algorithm, or a relaxation of this algorithm, that allows you to compute something very similar to the free energy in a way that is much more efficient. And for that, what we are going to do is provide a relaxation that is going to essentially exploit some of the properties of the system that I'm considering here. And we can do this in a very general framework. This is something that is called Markov entropy decomposition. We can do this in a very general framework, but here, for simplicity, I'm just going to do it in the simplest possible framework, which is we have 4 sides in a one-dimensional chain, okay? So simplest possible way. And now we are going to take a Hamiltonian that is finite range, as I was saying before, but finite range in 1D is the same as saying just 2 local. So it's just something that can be written as H in AB plus H in BC plus H in CD. Okay? And then we can rewrite this variational problem as this expression that I'm writing here. So it's taking the minimum over density matrices supported in ABCD of this difference that I'm writing here. Okay, so let's see how we can relax this. So the first thing that we can do is use something that is very well known in this community, which is the property of strong subadditivity. Why? Because here we have a factor that is a von Neumann entropy of sigma in ABCD, which is a state supported in 4 systems. But now I want to reduce how many systems I'm supporting this state in. So essentially what I do is use a strong subadditivity to change this factor of S of sigma ABCD by 3 factors that are supported in less systems. Okay? So when I use this inequality, what I can prove is that this is lower bounded by taking the same minimum of the first same quantity. And now this second part is changed by this. So minus sigma in ABC, minus sigma in BCD, and plus sigma in BC. Okay, so this has already helped us with the second term that appeared in the variational problem. However, what do we do with the first term? Well, with the first term, we can exploit the fact that we have a local Hamiltonian. So we have a Hamiltonian that is a sum of these 3 terms. And that means essentially that now I can rewrite this trace by inserting this sum and then changing the support of each of these sigma by tracing out the corresponding part that is out of the support of the H, right? So that means that I can essentially rewrite this first term as trace of HB, sigma AB, and so on and so forth. And until here, well, so far so good. However, we still have a problem, which is that we are taking the minimum over state sigma ABCD that are supported everywhere, and this is precisely what we didn't want. But what we can do is further assume something that is a condition called of locally consistent marginals. And what this is telling us is essentially that if we consider now 2 density matrices in ABC and BCD, such that when you trace out the A part from the first one and you trace out the D part from the second one, what you obtain is exactly the same, which is something that now I denote by sigma BC for convenience, then now I can rewrite this problem as taking the minimum over this set. And of course, this minimum is going to be over a larger set, which means that the minimum is going to be smaller. So this goes in the right direction. Okay? And then I have rewritten the first expression that I had here in terms of a problem in which now I'm optimizing over density matrices that have more reduced support. This is pretty dumb when we do that only for 4 sites, right? Because we have reduced only 1 system in each of these. However, if you do this now for many sites, you see how much you're gaining. Because if you reduce n sites to density matrices supported only in 3 sites, you have gained a lot. And this is essentially what happens with this algorithm. So this is what we call the MED, what is called the Markov entropy decomposition. And this is something that was introduced by Poulan and Hastings in 2011. And essentially, what I have just shown you in the previous slide is that the MED is always a lower bound for the free energy, because we started with the free energy and we provided a relaxation, right? So now the question is, I have some convex problem whose minimum is going to be the free energy, and I have another convex problem whose minimum is going to be the MED, and I know that one lower bounds the other. But do we know how different this is? So if I compute the MED now, do we know if this gives us a similar minimum, so if it gives us a similar quantity to the free energy? And secondly, this is an algorithm. Do we have convergence guarantees for the algorithm? So do we have that this algorithm is efficient? Because otherwise it's pretty useless, no? And this is essentially the starting point of this project. So the first thing that I want to show you is a very simple case, which is the exact case. And this is the one that I want to present here because I think it's going to be the easiest to understand how this works. And essentially what this case is telling us is that for 1D local commuting Hamiltonians, the met is exact. So this is important. We are assuming now that our Hamiltonians are commuting. And let's further evolve from what I'm saying here. So I'm saying that the met is exact. And what this is essentially telling us is, first of all, that the minimum of the met is the same as the free energy. So we are really obtaining exactly the same value. And secondly, the algorithm outputs the exact marginals of the Gibbs state. And this is pretty crucial. You will see later why. So let's see the proof for this because it's really beautiful and it's essentially based in entropies. The proof is the following. I consider the Gibbs state, which is now the exponential of minus the sum of the Hamiltonian that we have here over the partition function, which is this set. And now, since I want to have the marginal of this state in ABC, I trace out the part in D. However, remember that I'm assuming that the Hamiltonian is commuting. This essentially means that I can rewrite this as taking out these two parts, so the exponential splits. I can take out the part in AB and the part in BC, and I only have here the part in D. So I have the partial trace in D of the last factor in CD. Then, of course, I can do exactly the same thing for the marginal in rho BCD and the marginal in BC. And I have these three expressions here, okay? And now what I will do for a second is write them in this box so that we don't forget how they look. And now I will consider an ansatz. And the ansatz I will consider is the following. I have the sum and difference of these three relative entropies for any pair of states, rho and sigma. And what I know is that this is always larger than or equal to 0. You can see this, for example, by taking data processing inequality in the difference between these last terms, and here just by using positivity of this relative entropy, right? And on top of that, we also know that this is equal to 0 if and only if all these marginals coincide. So all the terms that appear in all these relative entropies actually coincide. This is very easy to prove. Okay, so we are going to now use these ansatz with the marginals that we have here for the Gibbs state. And what we obtain is the following. So now we take D of sigma ABC, rho ABC, and we extract the von Neumann part of sigma ABC. And then in the second part, we just replace the value of rho ABC as it's written here, and then just by taking into account that logs of matrices and commute split, then we can rewrite this expression here. And we do the same for the other marginals, and then we have these three expressions that we have here. And now, of course, we want to put this back into the ansatz that we have here, which means essentially that now if we take the sum and difference of these three terms and further assume that we have locally consistent marginals, then that means that this term here, trace of sigma ABC minus HBC, this is going to be trace of sigma BC HBC, and this is going to be exactly the same term that is going to appear here as trace of sigma BC HBC, because we are assuming the locally consistent marginals assumption. So these terms cancel out, and this is why we can combine all the terms that appear here and reduce them to this expression here. Now that we have this expression, we use that by the ansatz that we have from above, this is actually larger than or equal to 0. And then, if you look carefully here, you realize that minus log of sect was the free energy, which means that we can bring it to this side, and now we have an upper estimate for the free energy. Okay, so the free energy now is upper estimated by this sum and difference of terms. However, if you look here to the met that I'm keeping at the top of the slide, this is exactly the same expression that we have there by taking minimum. So now we take a minimum, and what we have is that the free energy is upper bounded by the met. But I just proved a couple of slides ago that the met was actually upper bounded by the free energy, which means that in this particular case, both of them are the same. Okay, so this is the way to see that in this case, the met is actually exact. This is the way to conclude it. But apart from that, I told you something about the marginals. And to see what happens with the marginals, we have to go back to the case of equality to 0 in the ansatz that I was suggesting before. And this equality to 0 comes if and only if we have equality in all these pairs of marginals, which means that the output of the met, apart from the free energy, is going to be these three marginals of the free Gibbs states, so rho ABC, rho BCD, and rho BC. So now we have an algorithm that is essentially giving us the free energy and these three marginals, but we are interested in obtaining the Gibbs state itself, not the marginals of the Gibbs state. So the last part that is remaining is to merge them. And the way to merge them is the following. If you have Gibbs states of local commuting Hamiltonians, we know that they are quantum Markov chains. And this is crucial, because now we are going to use that we can merge quantum Markov chains. We have a quantum Markov chain defining ABC, and another quantum Markov chain defining BCD, such that in the BC part, they exactly coincide. Then it's very easy, this is an exercise, it's very easy using PETS recovery maps to realize that actually you can merge these two quantum Markov chains into a quantum Markov chain between A, B, C, and D, and the same between A, B, and C, D. And this automatically yields a quantum Markov chain in A, B, C, and D that is actually automatically the Gibbs state, the global Gibbs state drawing A, B, C, D. So it's a very nice proof. So what I essentially told you here is that in the exact case, you recover completely the Gibbs state, which is really nice. And now we can write this in an algorithmic way. First of all, I was doing this for 4 sites for simplicity, but of course this automatically extends to multiple sites in 1D just by considering this extended method, which is essentially the same thing as before, but now, well, with all the systems that appear here, and the ansatz is also totally analogous, and you can prove by induction exactly the same. And once we have this, we can write the algorithmic version of this. And the algorithm that one obtains is essentially the following, that for 1D local commuting Hamiltonians, there exists this algorithm that takes as an input the HX, so the terms that compose the Hamiltonian, and outputs the free energy and the marginals of the Gibbs state in subsets up to a constant size. And this is output as, up to an error epsilon in a time that is polynomial on the system size and polylog on 1 over epsilon. Okay. So this is the exact case. And now in the last part of the talk, what I want to do is actually expand in the non-trivial cases. And the non-trivial cases are quite non-technical, quite technical, but I want to give you here an intuition of what is happening. So essentially, in those cases, since the decomposition is not going to give us an exact an exact value of the free energy, what we need to find is the case in which it gives us an efficient approximate version. And for that, what we consider is the following picture. So we consider now a lattice lambda and a subset A of this lattice. And the first thing that we realize is that if we consider the Gibbs state in lambda and trace out the complement of A, so if we take the marginal in A and we take the Gibbs state in A directly, these two quantities are in principle totally different, right? So this is something that is very clear for anybody that has ever seen this kind of Hamiltonians, that these two quantities in principle are going to differ a lot. However, we might be wondering if these quantities can be more or less alike in a certain sense. And this is what we do here. So what we do is consider something that we call the parent Hamiltonian of the marginal, which is just something that we denote by H tilde A, such that this local Gibbs state, so this marginal of the global Gibbs state in A, can be written as e to the minus H tilde A over the partition function. Sorry, this should be trace of e to the minus H tilde A. And then what we are asking is, if we take this difference between this H tilde A and the original HA, is this difference too large or not? So this is something that is called exact effective interaction. And we are going to see whether this can be decomposed into local terms whose norms decays exponentially with the size of the support. And in the cases in which we have that, we have actually gained. So for that, we consider this, which is a bit of a nightmare, but this is something that is called an exponentially decaying effective interaction. And I don't really want you to follow completely the details of this definition. I just want you to get an idea of what we are doing here. What we are doing here is essentially the following. We are considering something that is called HF super A, which is a sum of terms that have support, each of them has support in the intersection between A and X, and they satisfy a bunch of conditions. So the first one of them is that this is not too far from the HF exact, so this is smaller than a certain epsilon. Then we need that each of these interactions vanish if the relation between A and X is not good enough. And by this I mean if X is in lambda with a diameter that is too large, so larger than this L in particular, or if X is not contained in A, then this term also vanishes, or if X is contained in A, but it's actually so small that one side is too far from the complement of A. In that case, these terms also vanish. And finally, what we also say is that if you consider one such X, which is contained in this A, and you append something outside that is too far from it, this doesn't change at all. Okay, so these are the rules that we're following here. It's not extremely important that you fully understand what these rules mean, but what is important is that now we're going to require that we have an exponentially decaying effective interaction. And what it means is that the epsilon that we have here needs to decay exponentially with the factor L that we are writing as a second input. We allow for some linear dependency on the system size, and that's totally fine. But the important thing is the exponential decay with L. Okay, so now I know that this part was a bit messy, but you can forget about this, because the only important thing that we need is that we have examples for this property, right? And the first example that we have is that any 1D finite range Hamiltonian has an exponentially decaying effective interaction, okay? This is something that was proven by Kuwahara, so at least we have a very large class of examples here. And then the second example that we have is that, this is a bit complicated, if we consider in any dimension a finite range Hamiltonian, and we further assume that it has commuting marginals, what does this assumption mean? It means that every time that you consider two terms in the Hamiltonian, or every time that you consider products of terms in the Hamiltonian with partial traces, I'm forgetting here an R and an S, sorry, then all these terms have to commute. If we assume that, then at high enough temperature, there is an exponentially decaying effective interaction. And this condition looks extremely restrictive, but actually any CSS code, for example, satisfies it. So it's actually not so restrictive. So toric codes and all this stuff satisfy it. So that's fine. And of course, you might be wondering, well, if you have these systems, can you actually prove for other systems that you have this exponentially decaying effective interaction? And, well, up to 2020, it was believed to be the case. So in this paper, it seemed that it was proven that this result here could be extended to any dimension finite range Hamiltonians at high enough temperature without this commuting condition. However, there's a flaw in the paper, and up to now, no one has managed to solve it, which was part of the reason that we proved this. So I don't know, maybe it's the new time problem or something, in case anybody's interested. Because now it's been open for a few years. So I think there's hope that this can be proven for many more systems. It's just that mathematically, for the moment, there are no tools to prove it. Okay, so what is the first thing that we can prove from this assumption of exponentially decaying effective interactions? Well, the first thing is that if we consider now the Gibbs state of a Hamiltonian, then for any three disjoint subsets, we have an exponential decay for the conditional mutual information. And if you have followed this whole field of decays of conditional mutual information in the past few years, there have been many people working on trying to provide results in this direction. Actually, you see a lot of very recent papers that go more or less in this direction. This result is slightly different. And one of the nice things that it has is that we don't need B to be between A and C. So you can have B like here, for example, shielding everything here, and this not depending on the green part. No? So we have a bit more freedom with the geometry that we obtain. Of course, we have to assume the exponentially decaying effective interaction, so this is kind of restrictive. But this is not directly what we are interested in this project. What we are interested in is the free energy. And what we obtain in this case is the following. I'm reminding you here what the form for the MED was for the 1D chain. Again, I want to emphasize all the time that this is extended to much more complicated geometries. I just don't want to do it here because it's a mess. But just so that you keep in mind the expression that we have for chains, what we are proving in this theorem is that if you consider a Hamiltonian that is defined on a lattice of n sides, and this has an epsilon L effective interaction, then if we consider subsystems of a certain size, which is 5L, which is something that appears during the proof, then the free energy and the MED are actually pretty close. So are close up to 2n epsilon, so essentially something depending on epsilon. And moreover, the marginals returned by the MED are close to the original marginals of the Gibbs state, also by a function of epsilon. And this can be written, again, in an algorithmic way. So in this algorithm, I'm essentially writing exactly the same. And what I'm saying is that this algorithm runs in this time that I'm writing here. OK? So these are the convergence guarantees of the MED. So essentially, what we are doing is, in a very schematic way, we are taking the terms that compose a Hamiltonian. We are assuming exponentially decaying effective interactions. And then the MED is outputting this F tilde MED, which is close to the free energy, and these marginals of the Gibbs state, which are close, and these sigma A's, which are close to the marginal of the Gibbs state. So now the question is, can we somehow merge these sigma a's so that we can reconstruct something similar to the Gibbs state? And this is the last part of the talk. I know I'm running out of time, but just 2 minutes. For the last part of the talk, we have to use a rounding argument, which is also something that is very familiar to this community. We are going to use this rotated PETS map. So we have the PETS map that reconstructs BC from B, given in this form, and then including it in the integral with this weight. We define this rotated PETS map. And what we know from this paper from David, Andreas, and many more people, is that the conditional mutual information is lower bounded by 1/4 of a square of the one norm of the difference between the state and the reconstruction by this rotated PETS map. So if you remember from a couple of slides ago, I told you that if we assume exponentially decaying effective interactions, we have this exponential decay for the CMI, which means that now if you put these conditions together, we have that the difference between the state and the rotated PETS map can be upper bounded by something that decays exponentially with the distance between A and C. Now with this, we can construct a rounding argument. And again, this can be extended to Markov shields with a very weird geometry, but I do it here in 1D because it's much easier to see. What we do is take the state sigma A1, A2, and now we reconstruct from 2 to 3, and then we reconstruct the part in 4, and so on and so forth until we arrive at N, okay? And with this, what we have actually constructed is a sigma tilde that is very, very close to the Gibbs state sigma, given by this upper bound that we have here. So this is essentially how you can reconstruct something that is very close to your Gibbs state, complementing this schematic argument that I was saying here. So this is close to the Gibbs state up to a function f of epsilon. And with this, I essentially want to conclude just by summarizing all the things that I've told you here. And I think the best way to summarize is just by look at this scheme that I'm writing here, which is that you start with this exponentially decaying effective interaction. You prove that you have exponential decay of the CMI. You prove that you have a classical algorithm that is quasi-polynomial for the free energy and for the marginals of the Gibbs state. And using these two results together, you obtain efficient Gibbs sampling that is in a quasi-polynomial quantum algorithm. So, of course, there are many results related to this last part of efficient Gibbs sampling, but I don't want to details there. And there are many open questions from here, but maybe it's easier to take yours now. So thanks a lot for your attention.
So thanks, Angela. We have time for one short question.
Okay, just one short thing. Is the math free energy related to the quantum Gibbs free energy?
To the what, sorry?
Quantum beta free energy. Okay.
Sorry, I'm not sure what you're talking about. Yeah, is the math free energy?
Is the math free energy
Yeah.
related to the quantum beta free energy?
I don't know what that is, sorry.
Okay, that's fine.
I don't know, maybe it is, but I don't know.
Because that appeared in Pauline's paper when he was studying quantum belief propagation.
Then yes, I mean, this is the paper that introduced the math, so then for sure, yeah.
Then did you consider the situation when the overlapping local Hamiltonians are not commuting?
Yes, so we started from there actually, and this is something that we did for the 1D case, and this is why we realized that we needed something stronger as an assumption, because we couldn't get the exact case in that situation. So this is why we realized that what happens in 1D systems, for example, is that they have this exponentially decaying effective interaction, and this is what allows you to do a very similar argument to the one that you do in the exact case, but accumulating an error in each step that is very, very small. And then this is good because you accumulate this within this epsilon, and this is why you can obtain a good approximation. Okay.
All right. Do we have another urgent question? If this is not the case, let us thank Angela again.